Hello students, this is Dr. John, your physics and math professor, and today we're going to be talking about diverging mirrors and lenses. On the board here I've drawn an example of a diverging mirror with several different objects and a diverging lens with several different objects, and as we walk through this you're going to see that these are completely analogous to each other. They're very, very similar. If you understand the one, you will understand the other, and I've also drawn both of these at the same time on one study sheet and put that on the website. You can download it absolutely free. There's no cost or obligation. You don't even have to leave your email or register or anything. I want to be the go-to place for high school math and physics students to help you to get better grades. So please subscribe to this channel and check out my website. So let's get on with this video here. You'll notice that although this is a diverging mirror and a diverging lens, they have different names. This one is called a convex mirror. Why is it called convex? Because as your object's over here in green, comes in, light comes in from here, it hits the mirror, it's trying to get into the cave and it can't get into the cave. Remember, we talked about that in other videos. So it's vexed and it goes away, the light goes away, can't get into the cave, hence it's called convex. This one over here, I'll use this example down here. If we have an object here, the light from this is trying to get into the cave, it can get into the cave, so hence it's called concave. Actually, what I drew here on this side was two different concave lenses. This one over here would be called a simple concave lens, where it's concave on this side and flat on this side. This would still be concave because light's trying to get in. Often what we'll do is we'll take two of these and bring these together. So we'll put these together and we're going to get something called a double concave lens. That means it's concave from this side, concave from this side. It's completely symmetrical. You could look at it from the back side of the whiteboard or from this side over here, and it would be diverging if it comes from, light comes from this side or from this side. Now, why is it diverging? Let's take a look over here. Light comes from this point over here, follows this green line and reflects over there. If you're going from the middle of this arrow, you hit here, you would reflect over there. These rays diverge from each other. They don't come together in any way. So that's called a diverging mirror. And over here, the light from the top here comes up here, goes way up there. If you did this over here, you would hit the lens here and go this way. You diverge, you go away from each other. So that's a diverging mirror and a diverging lens. Let's go into the details now. Notice over here, the curvature of this, the center of curvature would be right over here. If you put a string over here with a pin, you could just follow this over here and you have the curvature of the mirror right there. And when we have thin mirrors and thin lenses, then the distance here from F is half the distance to C. So whatever, if this is say 10 centimeters, this would be 5 centimeters. I've drawn another F over here just to show a distance. There is no F on this side because the curvature would be on this side and the focal point is on this side as well. And the same thing here for this lens over here. If you put a pin over here, I've stretched this a little bit from this one because we don't need all this space. We need different spaces, allocations over here. The center is here. That would be the center of curvature here. You'd have to go way back here, the same distance, whatever this is, 10 centimeters or 20 or whatever this is here. You'd have that curvature here. You'd have the same curvature over here because you have this double concave lens. And the same over here, the F is half the distance to the C. We always measure from the center of the lens or from the center of the mirror. It doesn't matter. This distance here, because there's a very thin mirror, there's a very small curve. So there's really no difference between here and here, and let's say here and here. This would be practically identical for a thin mirror or a thin lens as well. Now let's look at the sign convention. We don't worry about C. C is just simply a number for the center of curvature. We worry about F. We worry about the focal point and especially the focal length. Now, the focal length, the focal point is where light should focus. It should come together there. Now, in this case here, light comes over here and it's reflected over there. Light from here would be going over there. It does not come together here, but it actually seems to be coming from here. Notice if you drew this light green line here that I had going back to the focal point, it seems to be coming from here. Well, light is supposed to focus at the focal point, not come from the focal point. So this distance from here to here, from the mirror to the focal point would be a negative. Let's say it's -5, whatever your problem would have. So this would be a negative distance to the focal length. That's very important when you're using the lens formula. We'll do an example of that in a minute. The same thing over here with a mirror, because notice the light comes here and it goes up here. It does not converge or come to a focal point. It seems to be coming from a focal point, the opposite of what you should be doing. So this distance here to the focal length, again, would be negative. Again, whatever your problem might be. -5 centimeters, -5 units is what we're going to do in this problem here. So a negative focal length, another way to remember it, any diverging mirror or lens has a negative focal length, but you can also see it there. And in the definition of a focal point, this is doing the opposite. Focal point is where light should focus toward. If it does that, it's a positive focal length. If it comes away from it, the opposite of what it should be, then it's a negative focal length. Now let's use a ray diagram and see what sort of images we get from these couple of objects. I've only drawn 2 objects here. You're going to see the pattern right away. I could draw a whole bunch of objects, but it gets really confusing. There's just too many lines here. So I'll take this object. Remember, the distance that or the height that we measure an object from is up from the principal axis as positive. If the object was like this, it would be a negative height. Or if the image was like this, it would be a negative height. Just like it should be. It's just very natural. So this over here would be a positive height as well. These images also have a positive height because they're upward as well. So let's take a look at the 2. Usually we use 2 rays. One is this light green one. It comes over here, reflects that way. But if we take a dotted line backwards, it's going to actually seem to be coming from the focal point right here, going that way. Then we take a second line, and for mirrors, we take the line that goes right to the center of curvature. Now, why do we do that? Because if you think about it, this light orange line here, if we take this out from the center of curvature, and then we continue on to the head of this arrow, this point right here will be at 90 degrees. It will be a normal to the mirror because the mirror is curved there, which means light that comes in here will reflect straight back. It will look like it's coming from the center of curvature here. That's why I drew a dashed line up here. And notice those 2, this green one here, right here, and this light orange one intersect right there. So number 1 is the image for this object over here. And number 2 over here, the first line is exactly the same. The green line is exactly the same. The other line though, it will come right up here. It'll come a little bit higher, again, hitting the center of curvature and going off that way. And this is the image right here, image number 2. You'll notice as the object gets closer and closer to the lens, the lines of intersection will be closer and closer to here. So as you're just about touching the lens, your image will look to be just about the same height. It'll just still be a tiny bit smaller. And as you get further away here, going to infinity, your image for this will still be inside this little green line. It's going to be a really tiny little image there. It'll shrink to infinity. As that goes out to infinity, this will shrink infinitely small. So you'll notice that all your images are inside this little green dotted line, and these are all virtual images. Why are they virtual images? There's a couple of ways you can remember it. The way that I like to remember it is these images are on the wrong side of the mirror. A mirror should create images on that side. Why is that? Because a mirror should reflect light. And this isn't reflected light. There's actually nothing here. Notice this is a wall. There's a wall here. There's nothing actually here. So these shouldn't be able to form images over here. There's virtual images because they're on the side where it should not be. So these are virtual images. They are upright images. Their magnification is less than 1 because they're going to be shrinking here from the original size. Now, if you go over here and you take a look, I try to put these images in sort of a similar location here. This one here I put inside F, just like I put this one inside F. If F is 5, this might be 3 or something like that. And notice they do almost the same thing. Here's the first one over here. I'll take this first line, goes over here, goes up to infinity, and we have a dashed line back to F, which is exactly the same as happens over here. Only here I use the light green line. Here I use the orange line for the focal point line. And then the other one will come here, and it will, this time we don't go through the center of curvature, we go through the center of the lens. The reason that we do that is because if we have a lens like this, and here's the principal axis, the curvature for a very thin lens is going to be pretty well flat right here at the center. So if light goes through the center here, it's not going to be twisted one way or the other. It's going to remain basically completely a straight line like that. So we can say that light going through the center will not change. It will not twist like this does over here. So we take the other ray of light, this blue one here, and we go right through the center and we see where they meet. Now notice here, the orange one, the virtual one for the orange one, the one that seems to be coming from the focal point, and this blue one here meet right here. So I have this one meets right here, and that's the image for this. And then the image for number 2, which I placed inside the focal length, ends up being right here. I just have to redraw the lines. I take this red one, draw it right through the center, and I meet right there. Again, as I come right close to the lens, I'm going to get my image right here. They're all inside this orange triangle made with the principal axis and the lens. So they start right here and they'll shrink down to 0, exactly like they do here. And notice all of them are between the mirror and the focal point. Here they're all between the lens and the focal point as well. Now notice on this side, the images are on the right side here. For the lens, the images are on the left side. Now why is that? Because both of these would be virtual images. These are virtual images as well. You would think for a lens that images should form on this side because light should go through a lens. But these are on the wrong side, so hence they're virtual images. I drew them in this beautiful brown color over here. And for a mirror, they should reflect to be real images. They're on the wrong side. So the wrong side of a mirror is this side, and the wrong side of a lens is the left side. So they're really sort of like reflections of each other. They're completely symmetric of each other, but this one here, just take this one, flip it over here, and you have this over here. And if you were measuring the distances here, the distance, say, to these images here, the distance would be negative. Why is that? Because they're on the wrong side of the mirror. Images should be on the reflected side of the mirror to be positive, so these distances here are negative. Same over here, images should be on this side, on the light going through the lens. They should be on this side, but light doesn't go through the lens. It does something weird here, so these distances here for the image are negative. And I'll show you an example here by actually doing a calculation. Let's just take this object over here, or this object over here, which is object number 1, and say that that distance, the object is, I don't know, 8. Let's say this here, f is 5 or minus 5. The distance here is 10. So this distance over here, the object, is equal to 8. It's less than 10 if we're saying that 10 is the center of curvature or the distance of curvature, then let's say that the object is 8. So let's use our formula here. 1 over minus 5. Why minus 5? Because we're saying the focal length is 5, or it's minus 5 in this case, is going to be equal to 1 over the object, 8, plus 1 over the image. Now to do the math on this, you can just simply plug these into your calculator. Be very careful with the negatives and with the fractions and stuff. Make sure you keep enough digits and all that stuff. Or what I can do here is find a common denominator. Notice these both would have 40 as a denominator. This would be minus 8 over 40 is equal to 5 over 40 plus 1 over image. If I take this 5 to this side, it's going to become negative. It's going to be minus 8 over 40, and then we're going to have a minus sign there. Minus 5 over 40 equals this. So this would be minus 8 minus 5, that's minus 13 over 40. I'm going to write that up here, give myself some more room. So minus 13 over 40 is equal to 1 over image. We can flip these both over now, and image is equal to 40 over 13. So the image is equal to minus 40 over 13, which is about negative 3.0. Remember we said the distances to the image are negative because here we're measuring it on the wrong side of the lens. Images should be on this side, so this distance will be negative. So this is going to be about minus 3 here, measured right here, which is about right. If this is 5 or minus 5, this should be about minus 3. And look over here as well, this over here, minus 3 to this first image as well. We could do the same calculation for the second object or for any object on here, and we'll get some distance here. They're going to all be negative, and they're going to be between 0 and minus 5, or 0 and minus 5. So I hope that helped. If it did, like, subscribe, and I will see you in the next video. I'll talk to you later. Bye-bye.